My name's Cory Isaacson. I'm the CEO of CodeFutures Corporation. We are the makers of DB Shards technology, which helps you to scale your databases in the cloud and otherwise, but most of our customers are cloud customers, and thankfully most of them are RightScale customers also, because it makes our job a lot easier actually. So I'm going to be talking to you today about how you can scale your database in the cloud, what some of the common practices are. So again, we make a product called DB Shards. For those of you who are interested, I wrote a book on software scalability called Software Pipelines. It talks about sharding and other techniques. But the reason I bring that up is mostly because we did that book based on a lot of research with Wall Street companies that had tremendous scalability needs in their applications. We worked with them at a prior company that I had, essentially helping them to scale for those applications. And no matter what we did, guess what the biggest bottleneck was? The database, all the time. And so that's really the reason for today's talk, is to cover those issues. We have some key partnerships, of course. We work very closely with RightScale. All of our products are packaged with RightScale technology as templates. We use RightScale monitoring to help us monitor our packaging and applications. It's very, very effective. It makes our job very easy. It works great for our customers too. We also work very closely with MyCloudWatcher to provide monitoring and management services 24/7. So between the three of us, we really have a very well-rounded offering to make sure that databases stay up. My guess is anybody here like database failures and just look forward to those days when you come in and the database crashed or didn't meet the demands. It's not very much fun. And I can tell you that we still get some of those calls in the middle of the night, and our product helps keep everything up and running, but it's always exciting when that occurs. So we do a lot of work in the high performance and scalability area. We have a lot of real world experience with our customers. Particularly with the advent of social networking and gaming applications. It's really amazing how much we see. And of course, one of the things that's really exciting about those applications is when are they most used? In the middle of the night for most of us. And so that makes it very, very challenging to keep them up. So what I'd like to do today is really, the objective is to provide you with practical information and tools that you can go out and apply right away to your individual environments. If you have other questions, we'll take some at the end, and then I'll be around afterwards also. So the challenges of cloud computing, first of all, the appeal of the cloud, I think you'll all agree, is that it's a very flexible model. You can scale it up and down as you want. You don't have to have a dedicated IT staff. We run some pretty enormous applications with some of our customers in the cloud, and it's really great because they have very, very minimal costs to be able to do that. No fixed costs. They don't have to plan on how many servers they need and things like that. They can just scale up as they require. That's, of course, pay as you go as well. But how many of you are working in the cloud now? Okay. Have you ever had a failure? Almost everyone, right? We see just in our customer base at least one failure a week now. And I say at least, sometimes more. And we see things where we see partial network outages, server failures. By nature, the cloud servers are made to be transient, so they tend not to last very long. I read one article on the internet that said that a very large company has never been able to keep a cloud server running consistently for more than 8 or 12 weeks or something like that. So it's not that it's not possible, and I'm sure that the infrastructure will get better over time, but you really do have to plan for that. It's very, very important. And then the other is disk volume issues. We see disk volume sometimes slow down or disappear or crash, and that's pretty bad if it's a database application. That's not good at all. Cloud-based resources are also constrained. You have a limited amount of CPU. You have very limited I/O rates. We believe that in what we've seen in physical data centers is we can get typically 5 times or more the I/O rates that we can from, let's say, EBS volumes in the cloud. So it's a huge, huge difference when you're talking about that type of capability. So you really have to be able to deal with these environments. So if we look at a typical application architecture, this is the way most scalable applications are designed. What we see is a front-end distribution tier. That's usually your load balancer. That's distributing the transactions across to a number of application servers. Then from there you go to your database tier. Very often people are using a master-slave type architecture where they're doing asynchronous replication, which is not terribly reliable, but it's a pretty typical architecture. And so when you look at scaling this, it's pretty obvious that scaling the load balancers is no problem. You can scale them a number of different ways. You can add more. They don't have any state in them. So that means if one goes down, it's no big deal. You could just start another one or reroute the traffic. That works fine. You can also use DNS services now. There's some very good services on the internet that will actually load balance across your load balancers, even across data centers or regions, in the cloud. There's all kinds of different things like that that are possible. Scaling the application server, that's also easy too. Same situation. You have a stateless environment typically. Even if you're using session data, usually it's not that much, and you'd only hurt a few users at a time if something went down. So you can add servers if your volume grows. One goes down, again, fail over to another. It's no problem whatsoever. But scaling the database is hard. So why is it difficult, and why is it such a challenge? Somebody was just asking me actually earlier today, why is it so hard to scale a database? And the reason is that, of course, the database is all about preserving state. That's what a database does, is it keeps all your information. The other is you have very large data sets. Try and take 100 gigabytes or a terabyte of data and move it from one disk to another disk, especially if it's in a database format, in 20 seconds or something like that. You just can't do it. So you have to be much more watchful of what really occurs. And so it really makes it almost like, it's almost like a locomotive that's full of freight that you're trying to move across the country when you try and do something with your database, and it never goes very, very quickly. And by the way, I've been working with database technology for a long time. I won't tell you how long because it'll date myself too badly. But the truth is that what I've seen is that the problems in managing large databases really haven't changed in their entire history. They're actually the same. Why? Because they're disk I/O bound, all of the other kinds of things. So we talk again that they're very I/O dependent. So if you do have cloud service failures, network or disk, you're going to run into a lot of trouble. And of course, if a database server goes down, that's the last thing you want to see when you get that call from the office or you come in the morning. So it's really not something you look forward to, because it's very, very difficult to recover from, especially if you don't have a good setup. So really, we see databases forming the last mile of true application scalability. It's always the biggest bottleneck in any application. It's the hardest problem to solve. But if you do it, and you do it successfully, that means that you can take your application to any level that you need to. And that's really what the goal is that we have. So there's an old saying all the way back from mainframe computers, which is that all CPUs wait at the same speed. So I don't know how many of you use RightScale management tools, but they're very good, and they will show you a picture that looks like this, where you have 80 or 90% I/O wait speeds. That means that most of the processor picture in this particular case is just waiting for the disk to feed something to the processor so that it can do some actual work. And that tiny little blue line at the bottom is what you see as actual productive processing for your application. So this is a kind of a worst nightmare picture. And this is a picture of an actual application that we worked on. It's a company called Family Builder. They have a top 20 Facebook application. They were one of the original Facebook applications. They grow something like 50,000 or 100,000 users a day. And before we started working with them with sharding their database, this is what their application looked like. It was really what they called the cloud I/O barrier. That's the name that they gave to it. But I think it bears repeating. They have a kind of an interesting story as an application. They started building Facebook applications in 2007 before it was popular at all. And they built this application, and they did some marketing the very first day. And they were in, by the way, a physical data center to start with. And they did their marketing the first day, and they got 30,000 users the first day. And the application promptly proceeded to crash, mostly because the database couldn't handle it. And they didn't allow for enough capacity and things like that. So they ran over to the marketing department and said, don't do any more marketing until we figure out what to do. So they scrambled with their data service provider, and we need more servers, and we have to balance this and do that. Anyway, the next day they came in, and guess what? They got 45,000 new users. And they went back to the marketing people. We said, we told you not to do any more promotion. And they said, we didn't. And so they really learned quickly that this is the nature of a viral application, right? So what happened was all of those 30,000 people referred more people than they even had the first day. And so the thing just, of course, promptly broke again. So they weren't able to handle it. So it took them about a year and a half, actually, believe it or not, of tuning the database and tuning their infrastructure. They moved it to the cloud. They did all sorts of things and everything they could do. And they finally got it to where it would work pretty stably, as long as they didn't do too much marketing. So they literally would go to the CEO of the company I know pretty well now, and they would go to the CEO and say, you can only do this many emails today and this many other things, because if you do any more than that, we're not going to be able to handle it. So they came to us and they said, we really know it's the database and we need to fix it somehow. And so that's where we implemented sharding, and I'll show you a little bit later what the after picture looks like, which is much, much better. But these are the kind of problems that you run into. We've worked with social gaming companies also. We have seen application growth like nothing I've ever seen in my career, where you go from nothing to 7 figures of users in a very, very short span of time. It's actually pretty scary actually when you're on the receiving end of all of that. So great for the business, but very challenging for the IT staff. So there are other challenges too with databases. We have to make sure that the data is consistent. We need things like ACID compliance and transactions. There's user contention. You have more than one user that wants to access the same information. That locking can be one of the biggest bottlenecks in any database application. And it's actually one of the earliest things you want to try and solve if you can. Operational challenges. What do you do if you do have an unplanned outage? Because you will if you're working in the cloud. Again, I said that we experience about a failure a week of one sort or another just within our customer base. And I'm sure we're a very small percentage of the number of total servers that are actually out there. So it's important that you have that covered. But I think what a lot of people don't realize is, what about planned failover? How many of you have ever had to re-index a database? Right? So indexes get out of sync. We had a customer today, literally, that ran into this problem where they said all of a sudden some query was going really slow. It used to work fine yesterday, and all of a sudden it was really slow today. And that was because the index got out of sync and the statistics were bad, and all of a sudden the optimizer couldn't do its job and we had to re-index. So if you don't even plan for that, you're going to have to take your site down. And we have seen customers who literally have not been able to touch their databases in 1 or 2 years because they're 24/7 websites and they can't take them down, and they're afraid, they're so big that they're afraid to reorganize any tables or do anything like that because it might break the whole thing. So it's pretty scary. The other is, again, if you have to, maintenance we talked about, space reclamation, but just the regular life cycle. What do you do for backups to make sure you can do them without taking the site down? What do you do for monitoring so that you know when there are problems? Application updates, of course, happen a lot. You want to be able to change things, version updates, upgrades, things like that. So those are all critical things to watch out for. So the biggest problem and why database scalability is necessary, especially in the cloud, is because databases don't slow down at the same rate, at an nice even curve. Have any of you ever had a database that got big and all of a sudden the performance just sort of went off a cliff? You ever seen that? This is exactly what the curve looks like. We ran this test on InnoDB. This was a very large, complex table, had a lot of fields, had a lot of indexes. And what we saw was that basically we could load 1 gigabyte of data in about a minute. We could load 3.5 gigs in about 12 minutes. 39 gig took 10 days, and we finally got tired of waiting. So it literally sometimes can get so big that you really can't do anything with your application. And this is very common where we see people trying to dump or load their database or reindex things or alter tables, where they literally will wait 24 hours or 36 hours to try and get it done in a test environment, see that it's not going to finish, and then have to come up with another strategy. So when you shard a database or when you scale it, you can basically turn this curve upside down and gain the exact same performance benefit. And that's what we're going to be talking about how to do. One thing I want to make clear also is that these challenges apply to any type of database. So most of our customers are using traditional relational databases like MySQL, Postgres, but the truth is that the NoSQL and specialty databases, which we really call in-memory databases, they're very fast because they run in memory, but don't think that they don't have the same problems. And the reason is, how many of you have seen that the NoSQL databases are adding more SQL-like features? Things like indexes, right? Those indexes work the same way that they do in MySQL. They're still tree-based indexes. They get more complicated as they get larger. As you add rows to the database, they're going to slow down exactly the same way that you see today. So really, you're going to end up with all the same things. You also, in those databases, have to do dumps to disk. You don't want to not have dumps. High availability is even more critical, I think, in an in-memory database, because if you lose it, you really lost it. You don't have anything to fail back to. Lifecycle management is also very important. So again, no matter what the technology is, big databases are just hard to manage. It's always been true. I think it actually always will be. I think as the technology gets better and we can go faster, we'll find reasons to make even bigger databases. That's what I've seen, throughout my career, is that they never really get smaller. And you can throw a couple twists in there. Is how many of you have ever seen an application-specific query or requirement totally bring the database to its knees? Anybody ever seen that? It's a very, very common problem, right? Some developer has to do something, he doesn't quite know how to do it, or maybe he does and it's just a complicated requirement. So you throw that into it, and then all of a sudden you really have other requirements that you just can't get around because of what your application has to do, and now you have real trouble on your hands. So we came up with, from looking at all this over many years, we came up with what we call the laws of database. They're really a little bit tongue-in-cheek, but I think true enough, which is that small databases are really, really fast. Big ones are really, really slow. So you should keep them small. That's the moral of the story. And if you can do that, you really can get performance that's probably beyond anything you've seen before. So what is the answer? The answer is database sharding. Database sharding is a technique for partitioning the database. I'll explain a lot more about it as we go through. But it's the only effective method for achieving scale, elasticity, and reliability and easy management regardless of the database technology you're using. It's the only way that we know to do it. It's incredibly practical and incredibly worthwhile. So what is database sharding? What you do with database sharding is it's a horizontal partitioning technique, which what that means is that you're actually taking objects or rows from your database and you're splitting them in some way across multiple different servers. So that's really the key to it. We want to see those rows, if you will, in the database split across. But one thing I think a lot of people miss is they really are looking for magical ways to do this or all kinds of other things. If any of you have seen this type of application that requires this, you'll know that if you have 100 tables in your database, how many tables are really big and highly active? Probably 5, maybe 10. There's usually very few tables that you actually have to worry about. The rest are all really easy. So what we can do is we can take those 5 or 10 big tables, we can come up with a way to shard them. In this example, we're talking about using customer number, which is a very, very typical way to do it. So you can see we've spread customer numbers across each of 4 shards, and we have the database across 4 different servers. And because of that, we can get 4 times or even better the scale. So what's the key to database sharding? Share nothing. That's really the key. And why do we say that? If you look at any paper and any study in computer science, you'll know that a shared nothing environment is the only way to scale limitlessly. If you do it any other way and you have common components like a common transaction controller, a middle tier, any of those kinds of things, they're going to slow you down. And any of you remember Amdahl's law from, anyway, well, maybe you don't, but I'll refresh your memory. But the idea is that you can't go faster than the slowest component is the basic concept. If you have any 2 components that are in a series, the slowest one will be the limit of how fast you can go. So that's really why you need a shared nothing environment. What do we mean by that is we mean independent servers that have independent disk, CPU, and memory to do a given job, and they're not dependent one on the other. There's nothing shared between them so that you can really get the biggest mileage out of each independent server and make it really go. So the way it looks in a sharding architecture is we have the application server tier. We have essentially a client driver typically in the application server tier. The client is aware of the sharding infrastructure. So the client knows where to go to get which information, which customers, again, are in which database. Then we have the sharding layer below that. And so each application server through its client can get to data on any of the different sharding servers. And that's the simplicity of how database sharding works. For some applications, this is incredibly simple. Some people are hosting customer data that's really isolated, almost like its own database. In that case, you can just have a separate connection to each one of those shards. And each customer lives in its own shard, and you can put 10, 20, 50 customers or 1,000 customers on one shard, and it works fine. In more complicated environments where the information is more integrated, then you have to do more sophisticated techniques of spreading the data out. But the concept itself is incredibly simple, and you can see how we have no shared components in this architecture to make it work, and that's why we can just keep adding scalability as we go. Now, in some architectures, though, we've seen a proxy be put in the middle between the application servers and the database servers. We don't really like this idea. I've done a lot of application development in my career before I ran this company. I don't really like the idea of something in between me and my database. You want to have a direct connection. Proxy servers can go down. You have to make them just as reliable as the others. They add cost, management overhead, and of course it's obviously slower if you're going through an intermediary to be able to do anything, so it's adding latency too. So we really try and have a direct connection as much as possible. So how well does sharding work? One thing we know is from a write perspective, it's completely linear scalability. This is an actual MySQL write scalability test on EC2. And what we see is we go from 2,500 writes, give or take, inserts a second, all the way up to 10,000 inserts a second, going from 1 shard to 4 shards. It works out very, very linearly. And we've seen this keep going and going. Why? Because the writes are strictly I/O bound. How long does it take? And so whatever the I/O is on one server, it's going to be 4 times as much on 4 servers. Very, very easy. On reads, what's interesting is we can actually have reads that are faster than linear scalability. So that's kind of interesting trick, right? But the reason is a couple of things. One is when you actually take your databases and split them up, they're much smaller, and so a much bigger percentage of the database and the indexes are in memory, and so the database server itself is just going to be faster. So we see sometimes we've seen very, very big improvements, even 100 times to 1 on the right side. It's really kind of amazing what you can do. So it really makes, again, everything much easier to manage. Also, if you take the same I/O picture and you look at any management that you have to do, you can see that you can do your management easily 4 times as fast also. Why? Because if you have to reindex or reload your database or any of those things, you're working with a quarter of the data. It's very, very, very simple. So again, why does database sharding really work? It works because we're really maximizing and changing the balance of memory and CPU per database size. That's the simplicity of it. If we look at how this goes, if you have a 100 gig database and you split it across 10 shards, and now you have 10 gig databases, and you have a 16 gig machine, you can see that the whole database for each one will fit in memory. Now that's not a requirement, but if you do that, you're going to see incredibly fast performance. Why? Because memory is about 100 times faster, particularly in the cloud, than disk I/O is. So you get just a tremendous speed up. But there's another factor I think that's less understood, and that is that the smaller the database, the fewer layers and less complexity there is in the index structure. And the index structure is almost everything. Index structure depends how fast your writes are. It depends how fast your reads are. It monitors really everything. And so when you have a smaller database, the index complexity is an order of magnitude less. It's not, in other words, a database that's 25% the size of a large database has much, much less complex indexes. Much, much more, it's much more than a 4-to-1 difference. And we've seen that over and over again. Again, there's no contention between servers. So what if you have lots of users? Each user is going to be, the user load is going to be spread out, so you don't have locking contention. You're not competing for disk. You're not competing for CPU, all of those kinds of things that are very, very common problems in managing a database. And it also allows for intelligent parallel processing where you can run queries on all the shards and roll the results up. We call that go fish queries. We have some tools that do that automatically and make it totally seamless to your application. But so basically, we can actually do roll-ups. For instance, how many customers bought a certain book last month? We can easily do that kind of query across all the shards. And again, because each shard is so much faster, it's much more than just a linear scalability type situation. So the goal, of course, is to keep those CPUs busy and productive. So this is the pretty after picture at Family Builder. So once we put them on just 4 shards in EC2, which we were hoping they would need more, but they didn't. But we put them on 4 shards. And you can see that now 85, 90, 95% of the CPU is actual user CPU. There's almost no IO8 CPU. They now, I'm happy to say, can tell their CEO to do as much marketing as they want to do as a company, and the system doesn't go down anymore. They can actually handle the load. They don't have to turn users away, in other words. And they have been consistently growing since we've implemented sharding at 50 to 100,000 users every single day, and it just works like clockwork. And again, we really thought they would have to scale to more shards by now, and actually 4 has been completely adequate, again, because of that multiple you get on the scalability side. It's really working out very, very well for them. So I want to talk a little about database types and how this really applies to sharding. So I'm sure most of you are familiar with the traditional database RDBMS platforms, MySQL, Postgres, things like that. They're very, very proven. They use the SQL language. If you don't like the SQL language, you can use object relational technology to map that and mask it. But the truth is they're very durable, they're transactional, they're dependable, but they're perceived a lot as inflexible. They're not as easy to change as some of the newer technology. So because of that, we see a tremendous interest in what we call the NoSQL databases. We really like to refer to those as in-memory databases because the reason that you're getting such great performance out of these databases is not really because they have a different language, it's because they're in memory. And we know that from very actual hard-won experience because we've tried some traditional databases that are in-memory SQL databases, and they're just as fast as the SQL databases. So the truth is, you can get the same type of performance. It doesn't matter what language you're using. It actually depends on the architecture of what you're using. So with NoSQL, there's all kinds of them now. We see a new entrant every few weeks, I think. I'm sure a lot of you have been reading about this, but they started out as key value stores. They are evolved to document databases, and now we see some that actually have some of both qualities. And they're very, very flexible tools. You can do lots and lots of things with them. Works out very, very well. So one thing I want to mention, though, before we go into sharding is the specifics of it, is there really are 2 types of sharding approaches that we've seen. One is what we call black box. And that's really an automatic approach, which I'll describe. And the other is what we call application aware, which is essentially defined by you according to your application. Both utilize the same type of idea. They're sharding on a data key, like we said, customer ID, something like that. That's typically how it works. Usually a modulus or some sort of consistent hash algorithm is how it's done. With black box sharding, what you're doing is you're attempting to shard everything evenly across all the shards. And one of the characteristics we talked about that's true in every application we've ever seen is very small amount of your actual tables or data structures need to be sharded anyway. So if you use a black box approach, what you're generally running into is you're sharding all of your tables, even though you probably don't need to shard 90 or 95% of them. So that really makes it's kind of wasteful actually, and it's not very efficient. The other is that the developer doesn't have any visibility or control as to how things are spread out across the network and the disk. And that's generally not a good idea because if any of you have worked in optimizing applications, if you can't control it or control that optimization, you're going to hit limits and you're going to hit things that you need to do specific to your application that aren't very easy to do. So the truth is it works acceptably for simple databases. It's fine if you're doing non-indexed NoSQL data stores. And the reason for that is they're really reading and writing one row at a time. So then it really doesn't matter how you're spreading things out. If you're reading one row at a time and you're doing it across the network, the speed is pretty much the same no matter what you do. But if you have to deal with result sets, anybody have to deal with result sets in their applications? Probably. Then it becomes much more complicated. And that's really where a lot of these tools get in trouble. So with application-aware sharding, this is defined by you as a developer or architect. So you actually take a look at your sharding. Again, pick what the large data is that you really need to shard, so you don't shard everything. You want to have explicit control over it. You want it to be tunable as the application grows because things are going to change. And it's going to be much more efficient for getting result sets. Why? Because the commonly accessed data is all grouped together in a single shard, and you can grab it in large chunks instead of having to just do it in one row and one object at a time. So how does database sharding work for a NoSQL database? Again, with single object reads and writes, it's very simple. You have the client. The client says, I want to add an object to the database. What happens is you call a put method typically. You give it a key and an object. Based on the key, it says, it goes in shard 2. There you go. You want to get an object out. You give it the key. It says, that's in shard 3. Bring me the object back. Very simple. Again, single reads and writes, very, very easy to do. One thing we've noticed, though, is that as people are trying to do more and more with NoSQL databases, they're finding that they do have to deal with result sets, and they're trying to figure out ways to do that. And if you look at some of the tutorials online about these databases, you'll see that the way they're doing it is they're actually putting the one-to-many relationships into objects. So you'll have a customer and you'll have all their orders in a single object, let's say. That's a good example of how it might work. And then if you have to get at that data or those lists different ways, you keep different copies different ways. And now all of a sudden you have a huge amount of redundant data, which is fine. But guess who has to manage that? The application code. So it all takes a lot of work and a lot of careful planning to be able to do that. So it's important to watch out for that when you select these choices. Now we think these databases are great and have fantastic potential actually, but don't try and use them for every problem or you're going to end up doing 10 times the work that you would if you just used a regular database for some tasks. That's something we've seen quite a bit of. How does it work for a regular relational database and an SQL database? This is a typical data model. It's a bookstore example. So what we have is we have customers buy books, which are managed by publishers, and then each customer has orders and order items. So we typically break a database down into 3 types of tables. We have the primary shard table, which is the customer table. That's the main table that we're sharding by. It then has shard child tables, which are the green tables. So we have orders and order items. The idea is that every customer, all its orders and all its order items are all in the same shard so that it's nice and organized. And when we want to get the information for a customer, we can find it all right away. So it's very, very simple. So that's what we talk about when we say application-aware sharding, because we want to be able to get that information in logical sets that mean something to our application. The blue tables, though, are global tables. So they really are small. They don't change as much, typically. You don't add a new publisher every day. You don't add books every second, usually. And so the idea there is that you can replicate those tables across all the shards, and that way you can be able to do complete joins and satisfy complete queries within shards as much as possible. So how does it work for SQL then? It's the same basic idea. You send a select statement, you get a result set back. Again, because we're talking application-aware sharding, that whole result set usually can be satisfied by a single shard. You get incredible performance that way. Then you have all of your write transactions, your CRUD transactions, and those essentially work the exact same way. You're writing those to a specific shard based on a key in the SQL. That's generally how it works. Yes? Yeah, that's a good question. The question is, how do you manage the global tables if they have to be on all shards, or should they be on just one shard? And the answer is it could go either way. And if you have to write them to all shards, you can do that from your application tier, but we actually have automated tools, of course, to make that automatic, and you don't have to worry about it. So you can do it actually either way, and there are good reasons to do it both ways. Depends how big they are, it depends what kind of joins you're doing, what kind of queries you have. Again, this is a very good example of how you want to tune your application and your sharding scheme to match the kind of things that you really need to do commonly. And if you do that, the performance gains are enormous. So what about cross-shard result sets? This will always happen in a sharding environment because why? You shard one way and you need the data another. And it's unavoidable. I don't care what tool you're using or what method you use. Any decision you make will only work a certain percentage of the time. So how do you do that? We call this, again, go fish queries. This is where we go out and we actually go across all of the different databases. We can do things like aggregate and sort on the fly, an incredibly fast streaming algorithm. With our tool set, we actually make this all seamless. But you can do it yourself as well. We've seen people do this in the client tier where they actually just bring the results back and assemble them on the fly. It's very, very fast if you do it right, because what you're doing is you're running the query and broadcasting it to all the shards at once. They're all running in parallel and doing all the work. So if you want to say, give me a count of customers by book or something like that for a month, that query is much, much faster and much, much easier to run on each individual shard, and then you can collate the results when you get them back. So it works very, very well. So again, more on cross-shard result sets. With a black box approach, cross-shard result sets are very difficult to do because the objects are all spread anywhere. There's no grouping to them, so they're not grouped by application-specific criteria. And that means that you have to get one row at a time from each different place and then assemble those results, and that can be very, very expensive. This is very common with the NoSQL engines. Again, it forces the use of denormalized lists, which makes a lot of work for the rest of us. You have to maintain it in application code. And as a sort of a partial solution to this, some of the products are now adding MapReduce capability, which is kind of nice, but it's basically an offline way of summarizing data into a format that you need. So it's not real time and you can't do things quite as flexibly. Again, with application aware, you have access to meaningful result sets of data, and the aggregation and sorts are much easier to perform because you have chunks of data that are coming back, not just small pieces. And again, logical search operations are much, much more natural in this type of capability. So I just want to talk briefly about high availability. We don't have too much time now, but I'll go through this rather quickly. But I think you all know that your databases are critical and you don't want them to go down. So you have to have a strategy for high availability. There's just no way around that. And a lot of people rely on something like MySQL master slave to do this and think that they're safe. The truth is they're not. If your master goes down, any transactions that are in flight, you're going to lose. So it depends on the rate of your volume, but we have seen it be significant, what you can do. And even in the MySQL documentation, for instance, they tell you that this isn't a reliable way to do it. But the other factor that a lot of people don't realize is it's not easy to do maintenance because it's very hard to fail over on even a planned basis the slave and the master. So even just to do routine work, how do you get the slave in sync, fail it over and make it the master, go do work on the master? That's a very, very difficult challenge. So when we talk about a sharding environment, we want to have at least 2 copies of each database on 2 active servers. We want a true active-active operation, meaning we can fail back and forth between either of them and have it be totally in sync with no penalty for that. If you're using in memory, you want to have 3 copies usually because it's so risky that something might go down. So it's much more challenging with that. And what you need to be able to support is fail down, fail over, maintenance, automated backup and restore, and monitoring. These are the critical things that really come with a good HA environment. When you have this, it's really nice because, again, we see failures just all the time now. And if it wasn't for our tool set, we would have had a lot of nightmare scenarios, I can tell you, on our hands. So we've been very, very fortunate. And I'm sure that some of you have read about some recent events where some people didn't plan as well as they should and ran into big problems on some pretty famous applications exactly like this. So you want to be sure that your HA architecture is very, very good. The other thing is elastic shards. Everybody's dream is to be able to have the database scale up and down just as easy as the application server. I can tell you that that will probably never happen, but we can get close. We have a concept we like to call shard mitosis, which means we take a shard and we split it into 2 shards, and then we can actually take that same 2 shards and roll it back into 1 shard later. But this doesn't happen in seconds. That's the point, is it does take time to actually implement this. If you have again, half a terabyte of data, you're not going to reshard it all in 5 minutes. You have to allow time. This is the real reason also for active-active instances and having a good HA environment. Why? Because you can take your secondary instances, go ahead and reshard your data on those, bring those up as the primaries, and you can do it all without taking the application down. So it's a very critical capability. Again, you can expand the number of shards, but you have to have a good HA environment. So I just want to talk briefly about the future, then I can take a few questions. I'll be around outside if any of you want to ask any questions afterward. But the one thing that we see is that there's a lot of new and great database engines out there, tons of them. There's a new one coming out, like I say, every few weeks we see now. And one thing we think it's really important is when you're designing your application and your data tier, pick the best one for the best job. And you may have to use more than one because the NoSQL databases in memory are very, very fast and very, very good for certain kinds of work. Traditional databases are still very, very good for lots of kinds of work. We've been using them for years reliably. Caching solutions are part of this as well. So you want to be able to mix and match these things so that you can really get the best performing solution for your application. They all need sharding though, so it doesn't really matter which environment you have and what they call it with that vendor. They're all sharded solutions. They really work with the same basic technique. And then improved management is really, really important. You want to be able to do configuration on the fly, monitoring. Again, make your shards as elastic as possible, even with the database concept.